Within industry, piping is a system of pipes used to convey fluids from one location to another. The engineering discipline of piping design studies the efficient transport of fluid. Industrial process piping can be manufactured from wood, fiberglass, glass, steel, aluminum, plastic, copper, and concrete. The inline components, known as fittings, valves, and other devices, typically sense and control the pressure, flow rate and temperature of the transmitted fluid, and usually are included in the field of piping design. Piping systems are documented in piping and instrumentation diagrams. If necessary, pipes can be cleaned by the tube cleaning process. Piping sometimes refers to piping design, the detailed specification of the physical piping layout within a process plant or commercial building. In earlier days, this was sometimes called drafting, technical drawing, engineering drawing, and design, but is today commonly performed by designers who have learned to use automated computer-aided drawing/computer-aided design software. Plumbing is a piping system with which most people are familiar, as it constitutes the form of fluid transportation that is used to provide potable water and fuels to their homes and businesses. Plumbing pipes also remove waste in the form of sewage, and allow venting of sewage gases to the outdoors. Fire sprinkler systems also use piping, and may transport non-potable or potable water, or other fire suppression fluids. Piping also has many other industrial applications, which are crucial for moving raw and semi-processed fluids for refining into more useful products. Some of the more exotic materials of construction are Inconel, titanium, chrome moly and various other steel alloys. Engineering subfields. Generally, industrial piping engineering has three major subfields: piping material, piping design, stress analysis. Stress analysis, process piping and power piping are typically checked by pipe stress engineers to verify that the routing, nozzle loads, hangers, and supports are properly placed and selected such that allowable pipe stress is not exceeded under different loads such as sustained loads, operating loads, pressure testing loads, etc., as stipulated by the ASME B31, EN 13480 or any other applicable codes and standards. It is necessary to evaluate the mechanical behavior of the piping under regular loads as well under occasional and intermittent loading cases such as earthquake, high wind or special vibration, and water hammer. This evaluation is usually performed with the assistance of a specialized pipe stress analysis computer program such as Caesar. In cryogenic pipe supports, most steel become more brittle as the temperature decreases from normal operating conditions, so it is necessary to know the temperature distribution for cryogenic conditions. Steel structures will have areas of high stress that may be caused by sharp corners in the design, or inclusions in the material. Wooden piping history. Early wooden pipes were constructed out of logs that had a large hole bored lengthwise through the center. Later wooden pipes were constructed with staves and hoops similar to wooden barrel construction. Stave pipes have the advantage that they are easily transported as a compact pile of parts on a wagon and then assembled as a hollow structure at the job site. Wooden pipes were especially popular in mountain regions where transport of heavy iron or concrete pipes would have been difficult. Wooden pipes were easier to maintain than metal, because the wood did not expand or contract with temperature changes as much as metal, and so consequently expansion joints and bends were not required. The thickness of wood afforded some insulating properties to the pipes which helped prevent freezing as compared to metal pipes. Wood used for water pipes also does not rot very easily. Electrolysis, that bugbear of many iron pipe systems, doesn't affect wood pipes at all, since wood is a much better electrical insulator. In the western United States where redwood was used for pipe construction, it was found that redwood had peculiar properties that protected it from weathering, acids, insects, and fungus growths. Redwood pipes stayed smooth and clean indefinitely, while iron pipe by comparison would rapidly begin to scale and corrode and could eventually plug itself up with the corrosion. Materials. The material with which a pipe is manufactured often forms as the basis for choosing any pipe. Materials that are used for manufacturing pipes include carbon steel, ASTM A252 spec grade 1, grade 2, grade 3 steel pile pipe, low-temperature service carbon steel, stainless steel, non-ferrous metals, for example cupronickel, non-metallic, for example tempered glass. Standards. There are certain standard codes that need to be followed while designing or manufacturing any piping system. Organizations that promulgate piping standards include ASME, the American Society of Mechanical Engineers, B31 Series, ASME B31.1 Power Piping, ASME B31.3 Process Piping, ASME B31.4 Pipeline Transportation Systems for Liquid Hydrocarbons and Other Liquids, ASME B31.5 Refrigeration Piping and Heat Transfer Components, ASME B31.8 Gas Transmission and Distribution Piping Systems, ASME B31.9 Building Services Piping, ASME B31.11 Slurry Transportation Piping Systems, ASME B31.12 Hydrogen Piping and Pipelines. ASTM, American Society for Testing and Materials, ASTM A252 Standard Specification for Welded and Seamless Steel Pipe Piles. API, American Petroleum Institute, API 5L Petroleum and Natural Gas Industries a Euro Steel Pipe for Pipeline Transportation Systems. EN 13480, European Metallic Industrial Piping Code, EN 13480-1 Metallic Industrial Piping, Part 1, General, EN 13480-2 Metallic Industrial Piping, Part 2, Materials, EN 13480-3 Metallic Industrial Piping, Part 3, Design and Calculation, EN 13480-4 Metallic Industrial Piping, Part 4, Fabrication and Installation, EN 13480-5 Metallic Industrial Piping, Part 5, Inspection and Testing, EN 13480-6 Metallic Industrial Piping, Part 6. Additional requirements for buried piping, PD Trail 13480-7 Metallic Industrial Piping, Part 7, Guidance on the Use of Conformity Assessment Procedures, EN 13480-8 Metallic Industrial Piping, Part 8, Additional Requirements for Aluminium and Aluminium Alloy Piping. EN April 3, 1993 Eurocode 3 a Euro Design of Steel Structures, Part 4-3, Pipelines, AWS, American Welding Society, AWWA, American Water Works Association, MSS a Euro Manufacturer Standardization Society, ANSI, American National Standards Institute, NFPA, National Fire Protection Association, EJMA, Expansion Joint Manufacturers Association. See also. References. Further reading, ASME B31.3 Process Piping Guide, Revision 2 from Los Alamos National Laboratory Engineering Standards Manual OST 220-03-01 ESM, Seismic Design and Retrofit of Piping Systems, July 2002 from American Lifelines Alliance website, Engineering and Design, Liquid Process Piping. Engineer Manual, entire document a Eurocent U.S. Army Corps of Engineers, M1110L 4008, May 1999. External links, Building Services Piping links at DMOZ.